Again, I sort of, okay, I've had them, finished.
After surgery, Deirdre will need a monthly vitamin injection and daily supplements for the rest of her life. And the surgery itself is risky.
Every surgical problem gets magnified because of the sheer bulk of the patients. It becomes much more difficult for the anaesthetist to secure the airway properly, to get intravenous access for delivery of drugs. There are issues to do with positioning the patient. You've got to have an operating table that will take somebody who may weigh up to 200 or 220 kilos. One of the big problems is clot formation in the legs. The problem with clots in the legs is that they can detach from the legs and go up to the lungs. And that's a really serious problem with people who are very overweight. I think the other issues are that if you get a problem after surgery, it's more difficult to fix it because of the weight of the patients.
I'll always have an issue with my weight, always, to the day I die probably. And it'll always be a battle. Even if I'm adjusting to new eating habits and stuff, it still will be an adjustment. It won't be a automatic thing. So the issue I have with my weight, I'll have forever. It's just, this is the way I'm tackling it now, and hopefully this will work for me.
Hugh, can you aspirate on the stomach there?
Yeah, certainly.
She's probably at the lower end of the size spectrum, really.
Scientists in Cambridge discovered that people who were unable to produce a hormone called leptin became extremely obese. However, this condition turned out to be very rare, and any hopes of a widespread cure faded. But what the discovery did give science was a greater understanding of how our brains control our appetite and the potential to discover other genetic causes for obesity. And that's what happened. The scientists here in Cambridge have made another groundbreaking discovery, and this time it could affect a far greater number of obese people.
So Daph, what did you do when you found out that leptin deficiency is actually quite rare in obesity patients?
Well, next we really wanted to see whether there may be genetic defects in other molecules in the appetite pathway that might be causing obesity in some of our patients.
Right.
And we were already learning about some of those molecules. And one of the key molecules that we were interested in is a gene called MC4R.
Okay, why that one in particular?
Well, we know it's a key receptor in the brain because when mice lack MC4R, they become severely obese.
Okay.
It's really a key part of the brain that controls your appetite. And so if it's not working, people have an increased appetite and are very hungry and may become obese. That's what we thought, at least.
Okay, what exactly is MC4R then?
It's actually a receptor. So another hormone comes and docks on that receptor, and it's triggered by leptin.
And once the hormone docks, it tells the brain, I'm full.
Yeah, it tells the brain to reduce the amount of food you eat because you're full.
So although the hormone leptin regulates our appetite by interacting with the part of our brain called the hypothalamus, it doesn't do this directly. Instead, the process happens through a series of steps known as the appetite pathway. MC4R is one of the steps on this pathway, and if it doesn't work, the message that we're full doesn't get through.
So how do you go about finding out whether some patients have a deficiency in this receptor?
Well, what we actually do is we start with the patient's blood sample, and then what we do with the blood is we extract the DNA from the blood. So next what we want to do is to pick up one specific gene from that bit of DNA.
Find the MC4R
Absolutely,
gene.
find the MC4R gene and almost sort of cut it out of your DNA so we can really look at it specifically.
DNA is a molecule found inside almost every cell in our body. It's like the instruction manual that makes us who we are. DNA is made up of individual genes, which are the specific instructions telling each cell what job it has to do. Genes are made up of 4 different bases, represented by the letters A, C, G, and T. Every one of our genes is a combination of these 4 bases.
The MC4R gene is made up of 1,000 letters, and each one has to be right and in the right order. So if we look at these letters here, what we see, this is actually from a normal weight person here, in this row here.
Okay.
And what you see is that you see a black peak, which is a G, then a green peak, which is an A, and then a blue peak, which is a C. So here we're looking at the MC4R gene, and the normal pattern would be a G, an A, and then a C.
Yeah.
But the line above is the sequence from a patient. And here we see a G, an A, and now instead of a C, if you compare, you see a blue line and a red line.
Okay, so there's a clear difference
Absolutely.
in the gene for the MC4R. between
So
the two
one
patients.
copy of the gene is changed in this patient.
Okay.
And that would be enough to prevent the receptor from working and cause the person to become overweight. 1 in 200 people who are obese will have an MC4 gene problem. This is 5 times more common than cystic fibrosis. And yet a lot of people, including a lot of doctors, won't have heard of MC4 deficiency.
Is it too early to ask you, how do you treat this problem?
Well, that's exactly what we're trying to find out, because the whole point of trying to find the reason behind a patient's obesity is to find a better way to treat them. So we're currently working on some treatments. We don't have specific drugs that are targeted to this receptor as yet, but we're working on that.
The discovery of the MC4R defect is a major breakthrough because it explains why at least 1 in every 200 obese people are unable to curb their appetite. Until the test for MC4R becomes widely available, Deirdre can't know whether she has the defective gene or not, and any treatment for it is even further away.
So the scope is in the abdomen now. You can see a bit of colon there. We're pushing gas in there to fill up the space. Deirdre is she's sort of at the lower end of the morbidly obese spectrum, really, I think. So it's not too bad. That's just fat carrying blood vessels to and from the stomach. So what I'm doing is trying to clear away a lot of that fat tissue with the blood vessels. The instrument I'm using seals them and then divides them at the same time. I'm going to start stapling the stomach now, so I know where the upper part of the junction of the stomach is. So we've got to make sure that it's completely disconnected there. So now we've got open space between the pouch and the normal stomach. Here's our stomach pouch, about the size of an egg. And it's disconnected completely from the lower part of the stomach, which is here. Now, that's the remainder of our normal stomach. That'll just sit there, minding its own business. I still have to join this loop, small bowel, up to the stomach pouch. That's the next step. But when it is joined up, food's going to come here, then go straight into the small bowel. So by bypassing about 1/6 of it, you reduce its capacity to absorb food. So we're going to open the pouch now. So that's into the stomach pouch. So I'm just about to connect the pouch to the small bowel. There are some people, I think, who probably are too big to operate on. There are some people who are too unwell from the established comorbidities to operate on safely. There are probably some people who are psychologically not going to cope well with surgery. The tricky thing is to work out who you shouldn't operate on, not who you should operate on. Now I'm going to join these two bits of bowel together. Getting a bit smoky. Take another stitch, thanks now. That's it. Hold on to that for me now. Eventually we get back up to this point. We've made the Y connection. So this loop here is carrying all the juices from the pancreas and bile duct, and of course all the juices from the stomach, so they got to go somewhere as well. And they're being allowed to mix with the food at this level, and the food continues on. And from this point on, the patient's able to absorb food normally.
As patients continue to go under the knife to lose weight, back in the lab, scientists continue to search for the so-called fat gene. Recent discoveries like leptin and MC4R only affect a very small amount of the population. But in April 2007, a major breakthrough revealed what scientists had suspected all along. An obesity-related gene does exist in the wider population. The gene in question is called FTO. Unlike the genes discovered by scientists researching leptin and MC4R, FTO isn't defective, it just comes in two different versions, one of which, called a variant, is more strongly associated with obesity. If you carry one copy of this FTO variant, as a third of the population does, you have a 30% greater chance of being obese than those without any copies. 1 in 6 people carry 2 copies, which makes them 70% more likely to be obese.
This is the first evidence of a common gene across most populations that definitely increases your risk of being heavier or lighter.
Hi, love. How are you, sweethearts? I'm fine. You all right?
Deirdre has been tested for the FTO variant and carries 1 copy. But research is at too early a stage to understand the connection between it and her obesity.
FTO is certainly one of the most powerful obesity genes, but it's definitely not the only one. There are others just about to appear.
What's really significant about the FTO variant is that so many of us carry it. This is a gene that's been passed down to us by our ancient ancestors through natural selection, survival of the fittest, or maybe that should be survival of the fattest.
You know, the difficulty is that humans are designed not to live in the 21st century, but to live in a cave. So we're wired up to conserve energy whenever possible. Our bodies are wired to store energy. And that's a major disadvantage when you don't live in an environment which encourages physical activity.
In University College Dublin, a European-wide project called LipGene is hunting down more genes related to obesity and its complications. It's headed up by scientists Mike Gibney and Helen Roach.
In LipGene, we assign people to 1 of 4 diets to figure out which diet is best for preventing characteristics of type 2 diabetes. And it was very evident that some people respond to the diet, as in their health profile improves, and others it doesn't happen. And we put that down to their genes. So we did pretty extensive genetic characterization, as in looked at some 800 genes to figure out, okay, which are the genes which determine whether somebody responds to this diet and gets healthy or not.
The significance of research like the LipGene project is that it could result in a future where we have very different visits to our GPs. In the future, doctors could use information on individual genetic makeup to help prevent people from putting on excessive weight and treat those who need to lose it.
The problem right now, it's a one-size-fits-all approach, that if you're overweight or obese, you know, you go on a caloric restriction diet, you go on an exercise program, or maybe you take medication. The issue is that everyone doesn't respond to a diet or exercise program the same. Hopefully we'll be able to identify genes or variations in genes. That's where I think the area of molecular genetics is taking us, is the ability to individually tailor treatment.
People will begin to accept that, yes, I do have the genetic makeup that makes me more likely to get obese than the next guy in the same environment. If I can tell you that you are going to get diabetes if you gain 2 more kilos, then people will listen a little bit more carefully than say, by the way, there's a chance you might get it.
The whole area is known as personalised medicine. So anybody would walk into their GP, they'd give a small sample, and from that you could do some genetic testing for common diseases. And then the GP would take into account that genetic information and also environmental information, such as your diet, your lifestyle, and also your family history. And from that you get a much more comprehensive understanding of the person and what they are at risk of. And with that information then you can sort of design a lifestyle, including nutrition and health approaches, which is specific for them, which is more effective in terms of promoting health.
The ability to read people's genetic makeup in order to prevent or treat illness is an advance that science should soon be able to provide, but it could open a Pandora's box of ethical issues, which go far beyond science.
You know, I think you're into a kind of brave new world situation there, and that's got problems for people. It's tough luck if you've got a set of genes that means that it's a tougher struggle for you to lose weight. That's very hard. It really is genuinely hard. May help them, but it may disadvantage them as well. How you control that information is going to be very important. Who gets access to that information becomes very important. And you know, a lot of people might say, well, okay, I'd like to know personally, but I don't want anybody else to have that information. One